Hello, everybody. So I had gotten somebody asked me a question about something in one of the recent quizzes, and it got me thinking that like instead of just answering the question for that person, I should make a video uh, just about the kinematic equations in calculus. Okay, so kinematic equations. We'll talk about what those are a little bit. I'll go through some vocabulary and talk a little bit about the scenario that we're matched up against when we're doing this. But let's say just to begin with, the kinematic equations are the equations that describe moving objects. Okay, and objects can move in two dimensions. That might be like up and down, or left and right, or three dimensions. Um, up, down, left, right, forwards, backwards. But for our class, we'll just do two dimensions. If you take calculus 3 someday, you'll learn about the kinematic equations in three dimensions. And as you can imagine, they're a little more complicated, so it's not something we're going to address in calculus 1. Okay. Now, like almost in every video, there's just a problem I want to show you, and that might be all you care about, right? You might not really be interested in what's all the verbiage that goes along with it. What's it all mean? Maybe you just want the problem, and well, it's a video, so you can skip forward to that point if you want to. But I think that this requires a lot of explaining and a lot of thinking and a lot of conceptual understanding. All right. Like for example, physics. I like physics a lot more than I like math. Truth is, and here's my favorite physics book. It's called the Feynman Lectures on Physics. Richard Feynman is a Nobel Prize winner, and it's not that I think that's going to rub off on me or anything, but I happen to really like these books. When I was learning physics, this is part of where I learned how to understand physics. It's part of where I learned what I know now. And if you look inside of it, here's the part of the book that is relevant to what I'm going to show you in this video. It's mostly words, okay? There's a lot to read and a lot to think about that's not equations and numbers. Sure, there's some numbers and some graphs and so on, and you'll see some equations, but it's mainly words, and I really do think that's the right way to go about learning physics. Okay. Anyway, all right. So here's the scenario: we have 2D motion, and we have a coordinate system. The coordinate system is what makes measurement and science and math possible. Physics is a quantitative science where we measure things with numbers and try to figure out what's going to happen. So something might be moving up and down, and we might have a coordinate system like this, and that's how we track the position of an object. We just note its location on this vertical axis. Maybe it's moving horizontal left and right, and then we do it that way. How we arrange the coordinate system is up to us, and whatever's convenient. Maybe the axis is going at an angle. That's fine. That's still two dimensions, right? No matter how I orient this axis and put location measurements on it, it's still just two dimensions, all right? It's not that it has to be up and down or left and right. It just has to be a line, okay? And there will be like 0 for the sake of convenience, we'll say somewhere, and then the positive numbers to one side and the negatives to the left, all right? We could like treat it like the number line. Okay, even though like at some point I've got to just get on with this and tell you what's happening, but we don't, I guess, have to include the negative numbers if we don't want to, but this is normally how we do it, okay? So that's the scenario, all right? That's what's happening. There's something moving, and we have a coordinate system imposed on that situation. And then as far as the concepts in math go, then we'll say there's this function s of t, position at time t, puts position as a function of time. And then something called v of t, which gives the instantaneous velocity at any time, puts velocity as a function of time. What's velocity? Well, it tells you how position changes with respect to time, right? I move from here to there in so many seconds or something like that. How is your position or how is your location changing as time changes? That's what motion is, right? So anyway, but it's instantaneous. And in other videos, I've talked about what the word instantaneous means, but it means that every instant I can tell you what the velocity is. And then a of t will be the acceleration at time t, also instantaneous. And acceleration is how the velocity changes with respect to time. So you see the connection here? They're all linked together. We start by just saying, well, position, where is it? Okay? And then if it's moving, how's the position changing? All right? And that's the velocity. But maybe the velocity is changing. Maybe it's speeding up or slowing down. Well, then we have acceleration. All right? So this is how that changes, and this is how that changes. And we could keep going. There are concepts beyond acceleration. We actually can talk about, well, how is the acceleration changing? But that gets pretty deep, so we won't do that right now. And as far as the math goes, calculus is involved in this. In fact, this is the origin of calculus, really. And that's that the derivative with respect to time of position is velocity, and the derivative with respect to time of velocity is acceleration. Okay, how position changes is velocity. It's essentially what this says if I was going to put it into words, and how velocity changes is acceleration. Okay. Now, at this point in the class, we've learned not just about derivatives, but about antiderivatives. And so you can flip these around and say, well, the antiderivative of acceleration is velocity. That's true, because the other way, the derivative of velocity is acceleration, is also true. It's just two sides of the same coin. Okay. And then we could do the same thing. We could say with, say, velocity and position. The antiderivative of velocity is position, well, because the derivative of position is velocity, right? So the whether I say it this way or that way, just sort of informally right now, is not that significant, right? Okay, but those are nonetheless true mathematical statements about these concepts. Okay, so let's talk about a little bit of fine print, a little bit about the signs, and give you some examples. And I think it's important to talk about signs because as soon as people learn algebra, then that negative sign starts confusing things. But let's say that, like, just to give some examples and tell you a little bit about what plus versus minus means for this stuff that I'm talking about. Let's say we've got this axis, and that's our position axis. That's where it all begins. That's our coordinate system. And I've got it labeled, say, in feet, like so. What if s of 4 is negative 2? What does that mean? It means that time t is equal to 4, let's say seconds. We can measure time in different ways, but let's say seconds. The object is right there at the negative 2 position. All right, that's what that means. So if the position were negative, it just means, well, it's at that spot where, 2 spaces left of 0. Okay. All right, so that's how you would interpret a negative there. But what if the velocity was negative? So consider this. What if v of 4 was negative 2? What would you say about that? Well, that would mean at time t is equal to 4, the object is moving left at 2 feet per second. Okay? So if the velocity were positive, it would be moving this way. And if the velocity is negative, it's moving that way. So at time t is equal to 4, it's moving left at 2 feet per second. Now, one thing you'll learn as you further your study of physics is that velocity tells us two things. It tells us the speed something's moving and the direction. The speed is just like the absolute motion through space. Like for every second, I move 2 feet. That's speed. But, left or right, that's direction. So velocity will give you both of those things. Speed and velocity are not technically the same thing. I know people might use them interchangeably as if they were the same thing, but they're not. Okay, so note there that velocity's got a negative sign, which tells me the direction being left, and it's got a number, which tells me that quantitatively, how fast are you moving through space? 1 second goes by, move 2 feet. Okay. What if the acceleration were negative? So say, what if a of 4 was negative 2? That would mean at time t is equal to 4, the object is slowing down at 2 feet per second squared. And those units there usually strike people as unusual the first time they see it. I'll talk about it a little bit. But If the acceleration is negative, then we're slowing down. And if the acceleration were positive, we'll be speeding up. Okay, I'll explain a little bit about why the signs there make sense. But first about the unit. So if I say the acceleration is 2 feet per second squared, what we're saying is, well, you're slowing down 2 feet per second per second. Okay, I mean, what would it mean to slow down? Would it mean something like that? Like for every unit of time, you slow down a certain amount. Okay, so for every second, you slow down 2 feet per second. So that's why it's got those units of feet per second squared, because it's like it numerically reads this way: 2 feet per second, feet over seconds. Imagine if you treated those symbols for my units, they're like numbers, like they were fractions. Then that would be like feet over seconds times 1 over seconds, which is feet over seconds times seconds squared. So that's why acceleration has units of distance over time squared, just universally. Okay, so that's what I consider to be a little bit of the fine print and so on. And you might think I'm rambling just on and on with the video, but remember, you can skip and so on. And remember my favorite physics book, where I think you can really learn physics. Well, it's mostly words, right? So there's going to be some talking in the video, and I'm going to quit apologizing for it. Anyway, so one more thing. And so this is where like the substance of the problem we're about to do comes in. If something is moving, and so let's say we have 2D motion, two-dimensional motion, if acceleration is constant, and let's say like it's this number a, okay, and it's constant, it's always the same, it's not changing, okay, then the kinematic equations for acceleration, velocity, and position take these regular forms. Like, in other words, we got formulas. If somebody tells you the acceleration in this situation is constant, then all right, we know what the kinematic equations are going to be. Okay, a of t is just going to be this number a, which is the acceleration. Well, why would that be? Well, I mean, if it's not changing, that at any time it's going to be that number a. Okay, and then the velocity will be a times t plus v naught. Okay, in this symbol, that's like a v with a subscript of a 0. And that number right there will need to be the velocity at time t is equal to 0. Can you see why it would need to be that? What if you put 0 in for t? What should this tell you? It should tell you the velocity when t is 0. Well, if you put 0 in for t, this is going to go away, and that's what you're going to get. That's why that number needs to be the velocity at time t is equal to 0. And then your position is going to be 1/2 at squared plus v naught t plus s naught. So again, that's an s with a subscript of 0. This number will be the position at time t is equal to 0. And again, does that make sense? Well, okay, so if I were to put 0 for t, this should tell me the position at time t is equal to 0. And if I put 0 for t, this will 0 out, and so will that. And I'll just get that number. So that number better be the position at time t is equal to 0. Okay. Now, another thing that you can verify is if you take the derivative of this, you'll get that. And if you take the derivative of this, you'll get that. That's how the calculus is supposed to work. And that's the calculus connection between kinematic equations for acceleration, velocity, and position. So let's do a problem now, all right? So here we go. I'll describe the scenario to you. Then we'll find a way to work it out. I actually don't think if you're okay with the background I gave you, I don't think the problem is that hard. I don't think the math is that hard. You might have to think quite a bit about the concepts I told you, but the math is not too bad. So suppose we have a balloon that's rising vertically at a constant speed of 15 feet per second. Okay, and when the balloon is 100 feet in the air, a lead weight is thrown vertically downward so that its speed at that moment is 5 feet per second. So like somebody throws this weight towards the ground. I say vertically, meaning not at some weird angle to the ground, straight down so that it coincides with, say, our coordinate system being straight up and down, okay? But just that when at that time they throw it, it's moving 5 feet per second towards the ground. That's what that says. Okay. So 2 questions. How many seconds till it hits the ground? And how fast is it going? Or what's its velocity when it hits the ground? Okay. All right. So to be consistent with what I was saying before, we have this motion in the coordinate system. So here I think, well, the balloon's going up vertically. We'll put the coordinate system vertically. Makes sense. And like the ground will be like at 0 on the coordinate system. We can do that if we want to. And then it's at some point it's 100 feet in the air, and so there's a spot for that and so on. But this is the ground, right? And the thing that's moving that we're trying to track is the lead weight that's thrown towards the ground from the balloon. Okay. All right. So how do we solve this? How do we figure out how long it's going to take to hit the ground and how fast it's going? And if you can get this one, you can get that one. That's why I posed the questions in that order. Well, how about this? Let's use these. Oh, I forgot to mention. Okay. We make this assumption. As when you learn physics, you make lots of assumptions that aren't completely true, okay? We're going to assume for falling objects that they have a constant acceleration of 32 feet per second squared, okay? That's not really true. The truth is, like a falling object, it will accelerate initially at 32 feet per second squared, but at some point, as it goes faster and faster, the wind resistance overcomes its ability to accelerate any further, and falling objects reach a terminal velocity at which they're not speeding up anymore. An easy example to think of that happening is if you have a parachute, you reach the terminal velocity fairly quick. A lead weight is not going to reach a terminal velocity very soon at all. So this is, to assume that, this lead weight is going to experience a constant acceleration is not an unreasonable assumption, okay? It's still an assumption and it's not entirely true, but, we got to start somewhere, and so this is what we'll do, okay? If you don't want to question that, don't question it, just go with it, all right? Okay. So how about this? Let's try to answer these questions through using the kinematic equations we know apply. I mean, I did say that we're going to assume that the acceleration's constant. Okay, if that's the assumption or the truth, then these are the kinematic equations. Let's use those. All right. So what are our equations then? A of t is, let's see, negative 32 feet per second squared. So we'll just say negative 32. It's constant. Why negative? Well, because it's actually slowing down this way. Okay. All right. It might be like moving faster and faster towards the ground, but in the fact that it's moving towards the negative numbers requires it to be negative. All right. Okay. So we'll say A of t is negative 32. Okay, that was the first kinematic equation, is that A of t would just be this number A, which is the constant acceleration. And then V of t would be negative 32t. And then what was that number? Plus V naught, which is the velocity at time t is equal to 0. Well, so that's kind of buried in this statement. So somebody threw it, and it was moving 5 feet per second. Its speed at that moment when they released it was this, okay? So it's moving 5 feet per second towards the ground. All right. Okay, so that's this embodied here in the equation. This says its speed at the moment when t is equal to 0 is 5 feet per second. And that's what this number needs to be. It's like saying v of 0 is negative 5, right? Okay. And then S of t, the position, that's going to be what? Well, remember, it's 1/2 at squared plus v naught t plus s naught, where s naught is the position at time t equals 0. So That's going to be negative 16t squared. Do a little math. 1/2 negative 32t squared. That's negative 16t squared minus 5t. And at the moment that, like, say I'm calling this moment when it's released, I'm going to call that t is equal to 0. Okay. So, all right, at t is equal to 0, the velocity is negative 5. What's the position? When the balloon is 100 feet in the air, a lead weight. Okay, so the when at t equals 0, well, it's at 100 feet in the air, so we'll say plus 100. Okay, so those are the kinematic equations that would apply. A of t is negative 32, v of t, negative 32t minus 5, s of t, negative 16t squared minus 5t plus 100. Okay, all right. So from here, how can we use this to answer these questions? Okay, I've got equations that track the acceleration, the velocity, and the position. How can I use that to figure out when it will hit the ground? Well, there's a number for that, right? Hitting the ground means what as far as numbers go? It means that s of t, the position, is 0. Okay, so if you've got an equation that tracks the position moment to moment, which is what this does, then I will take that and I'll set it equal to 0. And if I solve for the time, that will be the time when it hits the ground. So I get this. That's solved by the quadratic formula. So I kind of take it down this way. There's my positive answer out of the quadratic formula. It turns out that turns out to be about 2.35 seconds. Okay. All right, so I got that answer. How many seconds till it hits the ground? 2.35 seconds. Okay, all right. So, and then what's that second question? What's the velocity when it hits the ground? Well, okay, so remember, I've got an equation for position, velocity, and acceleration. I'll just, you tell me the time. This tells you the velocity. Just put the time in you want to know the velocity at, okay? So it hits the ground when t is 2.35 seconds. Put that into that formula or function for velocity. There you go. It's like negative 80.2 feet per second. What's the negative mean? Well, it means it's moving downward, okay, 80.2 feet per second. Remember, velocity gives you two things. Direction, okay, downward, and then the speed, 80.2 feet per second. All right, so I got impact the ground 2.35 seconds, moving at 80.2 feet per second. And I guess it did say velocity, so I should include the sign, okay? All right, I couldn't help but be a little bit curious. Well, how does that translate into miles per hour? It's not hard to convert it. So I went ahead and did that, all right? It turns out about 55 miles per hour when it hits the ground. Okay, so we answered it. That's how you do it. You just use the kinematic equations under constant acceleration. I guess I should say a little bit. I mean, I did say there's a lot of concepts in this, but why the acceleration negative if you say that the acceleration's constant at 32 feet per second squared? Well, see, if something's moving up, we'd say its velocity is positive. And if something was moving down, we would say its velocity was negative. Remember? The acceleration needs to be negative because say you are moving upward at 32 feet per second. If the acceleration due to gravity is downward, then, you might initially be moving up, but as gravity pulls you down, you're reducing your velocity by 32 feet per second for every second. So say you start off, you're going 32 feet per second up, but gravity's pulling you down. So in the next second, then you stop. You come to a stop. You slow down and you come to a stop. You take away 32 feet per second from your velocity. And then you got to fall back down to the ground. So you take away another 32, and that increases your velocity in the negative direction. I guess, to try to say it as simply as I can. Okay, we solved it. 2 questions. One situation, kinematic equations. 2 questions about time and velocity. So I wanted to get a little more mileage out of this question. So I thought I really should, like, without doing like 2 other questions, just talk about some alternate versions that this problem could take, or and how that would change the kinematic equations. So suppose that, let's say, like, same scenario, but I'll change this about it. The object is thrown vertically downward at 15 feet per second. Okay. Okay, think about it like this. So that means, like, somebody threw it from their frame of reference at 15 feet per second. All right. In that case, we'd have to consider that, well, the balloon's going up at 15 feet per second, but then you throw something downward, you project it from yourself at 15 feet per second. Those would cancel each other out, and the velocity at time t equals 0 would be 0. It's like it wouldn't be moving. And you can kind of imagine how that would be, like if you were rising in a balloon at 15 feet per second, and that you kind of gently pushed it downward so that it, like, wasn't moving when you released it. It's kind of like that. All right. So now, how's that different than the way I said it? Well, I said that it's thrown vertically downward, but like in a way that its speed at that moment turned out to be, like, that's just how fast it was going, all things considered. Considering the up motion of the balloon and the down motion of you throwing it, the end result is that's how fast it was going. All right. So I worded it in a way that that's just what v of 0 was. Okay. And then another version of that is, what if the object was just dropped? Like, what if somebody didn't throw it? They just let it go. Well, they are in a balloon moving upward at 15 feet per second, and their hand and the weight in their hand is also moving that same speed. And so for it just to be released, at that moment it's released, t is equal to 0, it takes on the speed of that total system of the balloon and the person holding it. So in that case, v of 0 is just 15 feet per second. Now, it wouldn't change any of the other math. You'd still use the quadratic formula and do all that kind of stuff the same way. But if the wording were a little bit different, we would have to take into consideration what v of 0 is a little bit differently. Okay, but nothing else would change, and other than that, the kinematic equations would be the same.